Okay, I am talking about cracking an egg and cooking the chicken. So basically what this is about, for those of you who think it's a culinary expose, I actually found a vulnerability in the PCI Express specification that allows you to break out a virtual memory on any system with PCI Express. So if that was just a soup of acronyms, here's a couple terms that'll add more acronyms to that soup, so we'll have real alphabet soup. So virtual memory, basically it's what allows a process to think it's running on its own, and it prevents other processes from interfering with it or hacking into the OS. The MCH is the memory controller hub. It's like the chip on the system that manages all that memory. Memory mapped I/O is basically a device or device registers that are mapped in as if they were in physical memory. It's newer and faster and better than Port I/O. Port I/O is like the legacy one that CPUs use to be able to communicate with old devices. More acronyms for those of you who have not had a fill. So TLB is the translation look-aside buffer. It's a cache that caches recently used virtual to physical address translations. We're going to skip over that one. So PCI configuration space is all the registers that configure all the devices on your platform. So if you have a graphics card, there are registers in there that you can use to configure that, and that's how your driver tells you how to use certain features of that graphics card. The ECAM is the extended configuration space for newer PCI Express devices, and then the CR3 register is a register on the CPU that tells the CPU where to look to do virtual to physical address translations. So a picture for those of you who don't like the acronyms, this is virtual memory. So basically your virtual address is on the top, so the first few is kind of like an offset for your page directory entry number. And then that gets combined with the CR3 value. It finds that lookup, and then it goes and ends up mapping in an actual physical page. You can add extra layers of indirection if you want. So if you're a hypervisor, you can add in a whole nother layer, or if you want to use 64-bit or smaller pages, you can add in up to, like, I think 9 levels of indirection, which is very slow. So that's where the TLB comes in. So basically, why do I care, right? So virtual memory is kind of a protective feature or a promise of the platform. Once you start up as an operating system and you control these page tables, you have control over the platform. Unless you can access the page tables, you're kind of locked out, right? You can't add mappings to the page tables because you don't know where the page tables are in memory unless you're the operating system. This is that chicken and the egg problem. But since we're going to be cracking that egg and then also cooking the chicken, we're going to basically break that thing. It also protects against many types of attack. So our goal, in essence, is to map in arbitrary physical memory, which requires modifying the page tables, which requires knowing where they are in virtual memory before we can change them. So we could be kernel shellcode, we could be live memory forensics, etc. So in this first scenario, we have ring 0 control, but we don't necessarily have control over the operating system. And we want to do this in an OS-independent way because architectural hacks are far more fun because you can't really patch the architecture. So we know where the physical address of the page tables are. That's in CR3, but we don't know where they're mapped into virtual memory, so we can't actually just access them. The operating system usually hard codes that, so if you're on Windows, you just basically go to C and all zeros, and then you have the virtual address. But I think those attacks are lame, so let's try to do it more fun. So our chicken and egg problem is the fact that we don't know where the virtual pointer is for the page tables, but we do know the physical. All right. This is a talk usually I give over 40 minutes, and so I'm trying to condense it down, so it's going to be fast. So what we need to control just 32 bits of memory at a known physical address. Oh, look at that. It's already giving me the red flag. I have a timer up here, you know, Klaus, right? So if we can get 32 bits of memory, we can bootstrap everything. So let's look at this PCI Express ECAM one more time. So Port I/O used to be how you configure PCI devices. It's very, very slow. You have to access it like no more than 1 D word at a time, and you had to send 2 requests per. You had to send an address to CF8, 0xCF8, and then you had to send the data to CFC. So it's very, very slow. So they came up with a way to access it faster for PCI Express, because PCI Express is faster. What ECAM does is it basically shadows those registers into physical memory at the MCH level. And the base address of this is stored in a PCI Express register, which you can access through Port I/O. So what do? We're going to create a page table entry, a single page directory entry that we put somewhere in PCI config space that we can use Port I/O to write to. And we also know the physical address of the base of all of PCI Express. And then we can mark it basically as present. That maps in our existing operating system CR3 value. We insert that using port.io, and then we try to figure out where that physical address is, and then we can basically set the CR3 to that, and we can recursively map in the operating system page tables, create a new recursive mapping that we know for those page tables at a known virtual address, and then be able to do whatever we need to do. So the issue is that if we're just writing to arbitrary registers in PCI config space, we might crash the system. Conveniently, Intel made a register called scratchpad data, which just says, do whatever you want with this. It doesn't do anything. So it's exactly 32 bits long, which is perfect. So thank you, Intel. And so now basically we're able to do that. And then we can use the PCI Express bar register to figure out where in physical memory. And we get this really nice recursive memory. So we're going to change CR3 to point, which is actually tricking the CPU into using device memory as its page tables, which should not happen. But thanks to PCI Express, that can happen. It won't trash the TLB because the kernel code is marked as global. The CPU doesn't realize it's doing anything wrong because it's just asking for memory from the MCH, and the MCH doesn't know why you're using that memory. And then it's going to look for the real page directory, the ones the operating system uses, to figure out where there's a free entry, switch back to CR3, back to the operating system, and continue on. But now we have a virtual pointer to the operating system address, and we can do whatever we want. And it's like 30 lines of assembly. You probably can't read that. It's really small. But basically, there's like 4 lines in that actually matters. And if you guys want it, I can send it to you later. So it's very complicated because you have to make sure that you're not like caching or going outside of your cache boundaries while you're doing it, but it's pretty easy. So why is this the case? It's a feature creep, basically. They kept adding more features and then didn't look how that might have gone back and changed some of the earlier assumptions. So the eCam is for higher performance, and obviously platform manufacturers always want to sell things that are faster and newer, and they don't necessarily look at how that might impact previous assumptions. This happens all the time. There's the SMM caching bug, the virtual machine side channels, etc. So if you want to do this, you can do live forensics. So if you don't necessarily trust the OS API to do memory, if you need full memory access, or if you want to, you know, for reasons, have kernel shellcode and you want to access full system memory and memory mapped I/O without calling any system calls that might be logged. So I complained to Intel about this, and they said, oh, don't worry, it's not a vulnerability because you already had kernel access. So let's see if in how many minutes do I have? Like 2.5? 1 minute, if I can go from this to ring 3. So 2 more terms, DMA, direct memory access, and ATA is the legacy disk access mechanism. So what you can do is you can use ATA DMA to basically tell the hard drive to write to memory at a known location. So you can either use that to overwrite the kernel or the interrupt vector table or interrupt descriptor table, but you need to actually be able to write to physical memory and have port.io. So you can use port.io from ring 3 as long as you have IOPL, which is something that like Xserver and stuff runs with. So you can actually set up a table in the eCam pointing to the memory address from which basically file you want to write to. You can write the payload to the disk, and then you use port.io to tell the disk, the DMA controller to read it, and that just happens by the disk outside of the CPU. So let's see here. This is what the table will look like, which you can just shove into the eCam, and then you can send those kind of bytes, and now you basically have full read-write access to the entire memory space from ring 3, and what you do with that is an exercise left to the reader. So a few caveats, VTD is on most systems and they can block DMA, and then also newer drivers are in AHCI mode, which is far more complicated to do. So conclusions, nifty trick, not exactly a security hole because you have to already have some level of access, but x86 is full of weird machines. New architectural features probably create broken invariants, and this is just one example. Intel's pretty cool, hopefully they can take a joke, and if you want more details in POC or GTFO 0x5, I have all the source code and a whole bunch of more details. So thank you.